In section 7.7, we briefly review a very advanced topic in probability called Markov chains. And what these do is essentially use a matrix to understand a changing system. So you can think of certain systems or situations as having the property that there's a fixed probability of change over time. Now, sometimes this fixed probability might be something we determine, and we might just be looking at what would happen if it was fixed at that value, or it might be permanently fixed. But for our cases, we assume it's fixed. Some examples to give you an idea of this. So think about if we ran a bus system. We could look at people that go to work, commuters, as either users of the system or non-users. So there's two states that a commuter could be in. And over time, that state might change. Perhaps we introduce a marketing program. And so a commuter who is a user could change states from user to non-user and vice versa. Same kind of idea with the library. I could have a regular percentage. I could say in this community, 50% of people are patrons of the library. And based on our past statistics, there's a 5% chance somebody will stop being a patron. And somebody who's not a patron, there's a 20% chance they'll become a patron. In other words, people in this system change states from patron to non-patron. And so again, and then the same idea, rural, urban. Are you moving? How are people changing from one state to another? And so this is a very big topic. We'll look at just some of the basics of it, but it uses some ideas that we've worked with before, which makes it interesting as just practice. And also, it's a very applied type of probability method. So what we'll do is I'll use some examples to introduce the basic ideas. And so the first idea is a state matrix. A state matrix represents the current situation. So for this example, we'll make a state matrix, and I'll point out some properties. This says, suppose an insurance company finds that in a given city, 4% of people were in an accident this year. We want to represent this with a state matrix. So states, we have to think of, well, there could be multiple, but for us, if we're interested in people that were in an accident, the two possible states would be accident or no accident, right? So a person in the city either had an accident this year or they did not. And so what a state matrix does is it takes that and it puts it into what you could call a row matrix. So they either had an accident or no accident, and the percentage of people who had an accident would be 4%. Therefore, the percentage of people who did not have an accident would be 96%. And this would represent the current state of this system. And so what we would look at is how do these states change year from year based on our given statistics? A couple things to note. This would have been equally correct to switch the two as long as I label it. And also notice that this is a row matrix which adds up to 1. The entries add up to 1 because it represents all possible states of the given system. So the state matrix is very much dependent on the problem that you're working on and the circumstances that you're working on. But once you decide an order, here I decided accident, no accident, you want to stick to that in general. So the question is, how do I use this to understand what the percentages might be next year or later on? Okay, so this is the same example, but what I've done is expanded a little bit. So it says, okay, 4% of people were in an accident this year. A study finds that if a person was involved in an accident in 1 year, there's a 20% chance they'll be in an accident next year. And if the person was not in an accident 1 year, there's only an 8% chance they'll be in an accident next year. What percentage of drivers will be in an accident next year or the next year? And we could actually ask for all kinds of years here. So there's two pieces to answering this question using Markov chains. By the way, this could also be answered using a tree diagram, but the tree diagram would get very, very large. And I'll explain that in a minute. But if we want to approach this with a Markov chain with these matrix ideas, what I would need is my state matrix. So we already found that earlier, 0.04 and 0.96. And remember, I did this in the order of accident and no accident. What we would need next is called the transition matrix. This is how the system is changing. And so you start off as accident or no accident, so this is your starting point. And this is where you end up. Notice I'm keeping the same order, accident, no accident, accident, no accident. This will be a 2x2 matrix. Now let me read starting with the second sentence again and show you how to fill this in, this transition matrix. So it says, a study finds if a person was in an accident 1 year, so they started accident, there's a 20% chance they'll be in an accident next year. So the probability that they'll stay in the state of accident is 0.2. So that's starting at A and ending in the state A. So that means that if they start in the state A, there's an 80% chance they'll end up in the state NA, or no accident. Okay, now the next sentence. If the person was not in an accident 1 year, there's only an 8% chance they'll be in an accident next year. So if you started in the state NA, there's an 8%, so 0.08 chance you'll end up in the state A. And that means there's a 92% chance you'll remain in the same state NA. And so then the question asks us, what will the state matrix look like next year? So some people would call this S0 and call this your initial state. And we want the next state. We want S1 next year, and then the next year would be S2. And so this is my transition matrix T. And so the way you answer this question is through multiplication of matrices. And this works through the same method that we used when we were going through tree diagrams. Essentially, what we've done is encode this tree diagram into the transition matrix. And that's something you can, of course, read about in the textbook. As far as just finding the next state matrix, what we do is we take the 0.04, 0.96 initial state matrix, and we multiply it times our transition matrix. And what you get out will be the next state matrix. And so it depends on how things move in time. We're looking at years, so this would be next year's numbers, assuming that this is the steady change that we'll see, and we're using that data to understand this system. So the next year would give me, and I did this multiplication earlier, 0.0848 and 0.9152. Now remember, this was accident, no accident. So what says what percentage of drivers will be in an accident next year? I would say about 8.48% from this piece right here. So it goes down based on these transitions. Based on this transition matrix, overall, actually it goes up. Overall, this will actually go up. Now the question is, will it go up forever? Will you eventually end up with 100% of people in an accident, right? That doesn't make sense. And it comes back to this. We'll talk about how we can determine when will this level out. Will this system always increase A and decrease NA, or what's going to happen with that? Now the question also asks for the next year. Every time you multiply a state matrix times the transition matrix, you get the next state matrix. So if I was to call this S1, then I find S1 times T, this will give me S2, and this will be the next year. So I suppose you could say in 2 years. So let me go ahead and do that. If I was to do that, I would say 0.0848, 0.9152 times that matrix T, and just to save space, I'll write T equals, and I did this multiplication, and I got 0.0902 and 0.9098. So to answer the next question, remembering that this is accident, no accident, this part right here would be 9.02%. So still an increase. Again, will that keep increasing? What will it level out at? We'll see later on. If I was to multiply this again and keep doing this, I would keep getting the next year's numbers, assuming that this, again, it assumes this change will be constant, right? Now, I think it's fair to say, how does this relate back to that tree diagram? I told you it's in the textbook too, but I do want to illustrate it a little bit. So let me just do part of this using a tree diagram and show you where it's coming from. So I'm going to erase all this and pretend I came at this fresh and say, okay, how would I approach this with a tree diagram? So think about it. Our first step is saying there's accident or no accident, right? This would be the initial year. Okay, so we had 4% and 96%. And then from accident, you could have another accident or not have an accident the next year. Same thing from no accident. And so this would be the next year in 1 year. So reading the problem, remember there was a 20% chance if somebody was in an accident, they'd be in an accident the next year. And that means there's a 90, so this would be 0.2. So that means there's an 80% chance they won't be in an accident. And if they're not in an accident, there's only an 8% chance they will be in an accident. So this was 0.92, right? Same information, notice, as a transition to matrix we had before. So to answer this first part, what percentage will be in an accident next year, I want to know how you get to here, right? And so to get to here, on either end, you either started off with an accident, so that'd be 0.04 times 0.2, so accident followed by accident, or you started out not having an accident, but you ended up in an accident, right? And so if you do this calculation, so 0.04 times 0.2 plus 0.96 times 0.08, I'm typing in the calculator right now, you get 0.0848. And that's the same value we had before. Okay, so why not use a tree diagram all the time? Why are we introducing this new idea? Well, go ahead and answer this question the next year. Now you're going to have to make your tree diagram accident, no accident, accident, no accident, accident, no accident, accident, no accident. And when you want to find all the ways to get to accident A, you're going to end up having 4 things to consider. Maybe that's not so bad, but what if I asked about 5 years? This will keep growing, right? And so this will get out of hand really quickly. Whereas with the transition matrix, since those probabilities stay the same every time, I can just multiply matrices, which is much more efficient, but does the same thing. And so that's why we use the matrices. But if you're doing a small problem, you can always check your work using a tree diagram that can help you understand things. All right, so let's look at one other one where we just look at it right from the start and answer a question using Markov chain. So this problem says there's 2 main internet providers in a certain state, N and G, being real vague here. Each year, G loses 5% of its customers to N, and N loses 15% to G. If right now N has 65% market share, what will N's market share be in 3 years? Okay, so we're saying, let's say you work for company N, I suppose we'll call it. So you work for company N, and you see this data that you're constantly losing 15% of customers to G. Obviously, that's bad in the long run. So the question is, you want to be able to present to people at the company what will happen in 3 years if this trend continues. Obviously, you're going to continue to lose customers, but then you are also gaining some customers from G2. So the question is, what will be the trend in 3 years? What will this look like? And then again, like we'll talk about later on, what will it level out at if it does, in fact, ever level out? So again, you need those 2 pieces. You need your initial state matrix, and you need your transition matrix. The 2 states for a customer, they're either with N or G. Those are the only ones we're considering. Once I pick an order here, I got to stick to it over here. So we know right now N currently has 65% market share. So this represents a current situation. So this would be 0.65, and this would be 0.35. Okay, so transition matrix. Remember, this is where you start. So you start with N or G, and then you end up the next year with N or G. Right? And this doesn't have to be years. This could change over weeks or months, but the numbers might be different, right? It depends on the situation. Okay, now I got to read this really carefully. It says each year G loses 5% of its customers to N. So if you started with G, 5% of the time you end up with N. 95% of the time you stay with G. Okay. N loses 15% to G. So if you start with N, there's a 15% chance you'll end up with G. And that means there's an 85% chance you'll stay with N. We want in 3 years, so in 1 year will be S1, in 2 years will be S2, in 3 years will be S3. So we'll go ahead and we'll see how that looks in a second. So the first thing I want to do is find out what it will look like in 1 year. So that will be S0, S0. Times my transition matrix, which I'll write down the first time, and after this I'll just write T. When I multiplied these earlier, I got the following. It doesn't look good for N. I got 0.57 and 0.43. So again, if you work for N, you can say, if this trend continues, by next year we'll have only a 57% market share. And you can make your argument about what needs to change. So this would be your S1. This is in 1 year. To find the percentage in 2 years, you want to multiply this new state matrix, so the 0.57 times the 0.43, times the same matrix T, so this same thing that we had above. Well, I did that a second ago too. And again, it's looking worse for N. I got 0.506 and 0.494. So again, you work for N, you can say, and not only that, in 2 years, we will only have about a 51% market share. Remember, you're sitting at 65% right now. And finally, if I want to find out in 3 years, I can say 0.506, 0.494 times T and get the following. 0.4548 and 0.5452. So within 3 years, they no longer have a majority market share, right? So here's N and G. And so to answer the question, the market share will be 45.48%. So if this trend continues, it does not look very good for them. And again, we'll answer the question of, will this continue to fall till it's zero, or where will it level out at? But right now, we can see that to find the probabilities or find the percentages, all we got to do is keep multiplying. And so you can keep doing this in your calculator and see the behavior over time. So as far as the multiplication of the matrices, you definitely don't do it by hand. You can do this on the calculator. It's very straightforward. And I would recommend doing that. And I'm okay with you doing that as well. And again, practice paying attention to, you have to use the new state matrix multiplied by T to get the next state matrix.